Hello. My paper is a multimodal predictive agent model for human interaction generation. My name is Bonny Banerjee. My co-author is Murchana Baruah. We are from the University of Memphis. The problem we are going to solve is to develop a model for forecasting human interactions using 3D skeletal data. Interaction forecasting is a challenging problem as the model has to learn how the behavior of one person determines the behavior of the other, spatiotemporal relations between different skeletal joints of a person, as well as the two interacting persons have to be learned for accurate prediction. The other challenge is, though a large volume of work has been done on predicting actions using 3D skeletal data of a single person, as well as predicting human motion in crowded scenes, much less has been done on predicting interaction for two persons using 3D skeletal data. This problem, if solved, is useful for applications such as video surveillance, human robot interaction, assistive robotics, and robotic surveillance. For the solution to this problem, we define the problem in a more general sense, which we call the prediction or the pattern completion problem. Let X be a set of observable variables representing an environment in n modalities, where each modality is a sequence. Given a partial observation of X, we define pattern completion as the problem of generating X as accurately as possible from its partial observation. At any time t, the objective for pattern completion is to maximize the log likelihood of X. As the solution, we propose an agent model for pattern completion that perceives from its environment, acts on its environment, and learns efficiently. To the best of our knowledge, the proposed agent is the first of its kind to interact with and learn end-to-end from two-person interaction environments with performance comparable to models without attention that uses significantly less sparse observations. We model the environment from the perspective of one of the interacting persons out of the two. The other person constitutes his environment. There are 3 points that are very novel about our model. The modeled person, which we will refer to as the agent, learns to sample or attend to the most informative or salient location of the other person's body using a saliency map at each glimpse. Sampling constitutes the proprioceptive signal for the agent. Taking into account the past observations and its learned knowledge, the agent completes the entire perceptual and proprioceptive patterns or sequences after each glimpse. The pattern completion component in our agent is a multimodal generative model where the prediction error is in a perceptual modality provides the observation for the proprioceptive modality. Attending the environment selectively introduces sparsity in the agent's observations, leading to efficiency. Here is an overall architecture of our proposed agent model. On the top, you see the pattern completion module, which is essentially a multimodal variational recurrent neural network that takes as input signals in 2 modalities. One is the perceptual sensory signal, the other is the proprioceptive sensory signal. The perceptual sensory signal constitutes of the visual information from the external environment. Because this is a human-human interaction scenario, so the perceptual sensory constitutes of the part of the other person's body. The proprioceptive sensory constitutes of the location where the eyes of the agent are looking at. Ideally, this should be the activations of the oculomotor muscles, but we assume that there is a one-to-one mapping between the oculomotor muscles of the agent's eyes and the visual environment that he is looking at. So, the proprioceptive sensory that we consider here is the location in the visual environment where he is looking at. So, these two are the inputs to the pattern completion model. The output of the pattern completion model is the entire perceptual or percept sequence and the entire propriocept sequence. From the sequence that is predicted, we calculate the error, which is the prediction error, and this prediction error is used for learning the pattern completion model as well as it is used for selecting the action. This error calculation gives rise to the saliency map, which tells us where the error is the highest. That information is sent to the internal body, in this case to the oculomotor muscles as well as to the muscles in the agent's body, because the agent's body also has to move, and then that again samples the other agent's body as well as the agent's own body moves, which goes to the pattern completion model as proprioceptive sensory, and this loop continues to go on. As you can see here, the error in the perceptual modality or visual modality gives rise to the proprioceptive signal, and that is one of the key ideas in this model. This is the objective function for the pattern completion model, and this is our recurrent neural network. I will not get into details. The only thing I would like to mention here is n is the number of modalities and big T is the total length of the percept or propriocept sequence. All the details are in the paper. Please go through it. Here are some of our pattern completion results from our model. This is the actual video of handshaking from K3HI dataset. This is the predicted video from 30% of the truth, ground truth given. So, 30% of the observation has been seen. This was 50%, 70%, 100%, and when the skeleton joints are being observed, they are being marked with the red dots. So, as you can see, a variable number of skeleton joints are being observed. Of course, when the 100% of the ground truth is shown, the prediction is almost accurate. The higher the amount of ground truth given, the prediction is going to be more accurate. The pattern completion for the same shaking hand from the K3HI interaction dataset is shown here in all the frames together, and you can see these lines, gray lines, which shows how much of the ground truth is shown, 30%, 50% and 70%. This is another random case, a random interaction shown, which is for exchanging objects from the SBU Kinect interaction dataset. Again, for 3 different cases are shown, 30%, 50% and 70% ground truth given, and the salient joints are marked red. In both cases, as we see, the prediction is quite accurate, given that this model is learning from the entire two data sets, both of which are benchmark data sets. Now, some numerical results. In our model, the number of salient regions, as we saw in the last 2 slides, may change at each time step depending on the prediction error. This has a number of advantages. Most importantly, this allows the sampling flexibility. So, we are not fixed to the number of joints we can sample. Selectively attending to fewer joints makes our model more efficient, because we are not fixing the number of joints that we will attend to. So, we can sometimes attend to fewer number of joints than given, sometimes we can attend to more number of joints, but this makes our model more efficient. We select the number of joints we want to attend to as needed. However, this makes learning to predict salient regions more challenging than trying to predict salient regions which are fixed. So, here is a table from the paper where we show the average percentage of saliency joints for SBU Connect and K3HI datasets for each interaction. This is the proportion of joints that are sampled from the observation or ground truth, as we see that our model samples less than 50% of the joints in a skeleton in all cases. Despite sampling a few joints and a variable number of joints, our model is able to predict the salient regions correctly most of the time, which is shown in the paper using the tables. For the SBU Connect dataset, for all the interactions, our model performs better than other prominent models in terms of the average frame distance for one's time step ahead prediction. For the K3HI dataset, we are the first to report the average frame distance on this dataset. Here are some related models to the model that has been proposed in this paper. Copies of all these are in my website. Thank you, and for more information, please do feel free to contact us.